Hey, welcome to the Explainer. Today, we're going to get to the bottom of a really core math concept, cubes and cube roots. You can think of them as the basic building blocks you need to construct way more complex ideas in math. So here's our game plan. First, we're going to nail down what a cube actually is. Then we'll learn how to run a perfect cube test and what to do with numbers that don't quite make the cut. After that, we'll work backward to find the cube root. And finally, we'll push past whole numbers to see how these rules apply pretty much everywhere.
All right, let's get right into it and lay the foundation. What exactly is a cube?
Honestly, the idea is super simple. When you cube a number, you just multiply it by itself and then by itself again, 3 times total. And that little 3 you see floating up top, that's just a bit of shorthand for the whole process. And this works for any number, positive or negative, it doesn't matter. Take 5, for example. 5 times 5 gets you 125. But check out what happens with a negative number, like -4. You do a negative times a negative, which gives you a positive, right? But then that third negative multiplication flips the sign right back, and you end up at -64. So here's the absolute key thing to remember. The sign of your original number, positive or negative, it always survives when you cube it. You know how squaring a number always gives you a positive result? Well, cubing is different. It keeps the original sign, and that is a really crucial difference.
Okay, so if any number can be cubed, what in the world makes a cube perfect? Let's take a look at the blueprint.
A perfect cube is really just what you get when you cube a whole number. So 216 is a perfect cube because it's built from this solid foundation of 6 times 6 times 6. But what if I just throw a random number at you? How can you tell if its structure is actually perfect?
Well, there's this awesome method called prime factorization, and it's a super easy 3-step process. First, you break the number down into its prime factors, those basic numbers that can only be divided by 1 and themselves. Then you try to group those factors into little teams of 3. If you've got no lonely factors left over, then bingo, you've got a perfect cube.
Let's see what this looks like when it works out. We break down 216, and what do we get? Its prime factors are 3 2s and 3 3s. See how neatly they form those perfect little triplets? Nothing is left over? That is the telltale sign of a structurally sound, perfect cube. But now, look at 297. We find a perfect triplet of 3s, which is a good start, but then we have a problem. There's this single factor of 11 just hanging out by itself. Since it can't form a complete group of 3, the whole structure is incomplete, so 297 is not a perfect cube. Okay, so now we can spot an imperfect cube from a mile away, but can we fix it? How do you actually complete one of these unfinished structures?
Think of it like a puzzle, right? If your number is missing a piece, how do we figure out the exact block we need to make the whole thing stable?
Well, if we break down 3087 into its prime factors, we can see exactly what's missing. We've got a perfect triplet of 7s, that's great, but we only have 2 3s. The structure is just 1 3 short of being perfect. So to fix it, all we have to do is multiply by 3. That completes the triplet, and just like that, the number becomes a perfect cube. We don't always have to add to the structure, though. There's another way. We can also make a number perfect by just getting rid of the extra leftover parts that are messing things up. So let's take 6750. Its prime factors have a triplet of 5s and a triplet of 3s. So far, so good. But you see that single factor of 2 just hanging around? That's the piece that doesn't fit. To make the structure perfect, we just divide that extra part out. Simple as that. So, we've learned how to build cubes and how to fix them. Now, let's learn how to take them apart and get back to their source, to find the root from which they grew. Finding the cube root is literally just the reverse of cubing. All you're asking is, what number, when multiplied by itself 3 times, gets me the number I started with? It's kind of like I gave you a finished building and you have to figure out the exact size of the original brick used to make it. And guess what? That prime factorization method we've been using is the perfect tool for this too. We break down 1728 and see it's made of 2 triplets of 2s and 1 triplet of 3s. To find the root, just pull one number from each triplet. A 2, another 2, and a 3. Multiply them together and there's your answer. 12 is the cube root of 1728.
All right, we have totally nailed the basics with whole numbers. Now let's see how these same rules hold up when the structures get a little more complex.
Now, you might be thinking the rules are going to get really complicated, but the amazing part is that the core logic stays exactly the same, whether we're dealing with products, fractions, or decimals. For product, it's actually beautiful how simple it is. If you need the cube root of two numbers multiplied together, you can just find the cube root of each part on its own, and then multiply those results. It lets you break a big problem down into smaller, way easier ones.
And the logic for fractions? It's identical. Don't let the fraction bar scare you. Just find the cube root of the number on top, and then find the cube root of the number on the bottom, separately. Your answer is just a new fraction made from those two roots. Decimals can look a little tricky, but I'll let you in on a secret. They're just fractions in disguise. The key is to just turn the decimal into a fraction first, and once you do that, well, you already know the rule from the last slide. It's that easy.
So really, when you think about it, by learning to build, test, and deconstruct these cubes, you've gained a key to understanding structure itself. This isn't just about cubes, it's a whole new way of thinking that helps you see the hidden blueprints in all sorts of math problems. Which kind of leaves you with one final question. What other structures are out there just waiting for us to find the right key?